we present HVH, learning a hybrid neural volumetric representation for dynamic hair performance capture. This is a joint work with Carnegie Mellon University, Meta AI Research, and Meta Reality Labs Research. Building a realistic virtual head avatar from light stage capture data has long been an interesting problem with applications in many VR/AR related fields like virtual shopping, creating CGI movies, and enabling virtual telepresence. As one of the most important parts to establish identity in a head virtual avatar, hair plays an important role in appearance and personalization. Although many hairstyles are moving rigidly with the head, where we could simply model them as part of the head, there are also many hairstyles that are loose and may move differently with head. The complex geometric and dynamic properties of hair is one major reason that makes it hard to be dynamically captured compared to head. Thus, we present HVH for better hair dynamics modeling with good appearance. In this work, we separately model hair and head by a hybrid neural volumetric model of get hair and tracked mesh plus volumetric primitives. The model can be driven by sparse signal like a tracked head mesh with get hairs, which is later regressed into volumetric primitives that are attached to them. Each volumetric primitive will cover a local region around its attached vertices, and several local regions fields are learned inside each volumetric primitives. The hybrid model can be rendered with faithful rendering results and reasonable runtime performance with our volumetric remarching algorithm. There are two stages in the whole pipeline. In the first stage on the left, we perform get hair tracking as a per-frame optimization problem. Given multi-view optical flow, we construct data term objective to regularize hair flow. Meanwhile, reconstruction loss on hair shape is added to solve for possible future hair shape. In addition to data terms, model terms on hair strength length and curvature are applied to preserve hair strength geometry. In the second stage, we learn an autoencoder that transfers from sparse signals like head tracked mesh and tracked get hairs to dense local volumetric radiance fields. The whole model is learned with multi-view RGB and optical flow with differentiable volumetric remarching. We compare our method with nerve-related methods and MVP on our hair dynamic data for novel synthesis, and we found our model could achieve the best rendering quality with details captured. Here are some results on other sequences. In our ablation study, we further found that better tracking and flow consistency could improve the generalization of our model, where we found our model improves more on unseen sequence and infers more consistent hair shape. Thanks to the good initialization from tracking, our model is also less affected by noise from off-the-shelf methods. On the tracking side, our tracking method achieves the most smoothing results when applying all regularization terms on length and curvature, and it could be unstable if either of them is missing. Our method also supports various applications like freeview drivable animation when given appropriate driving signal and could achieve moderate level of hair editing. Thanks for listening, and see you at our poster if you are interested and attending in person.